All right, good afternoon. Sorry that I couldn't be there with you guys today, but we're going to go ahead and kind of look through some things about sound. So, the first thing that we're going to look at is the warm up question. And the warm up question is, which ways can humans see into the human body? So I want you guys to brainstorm with the people at your table and kind of talk through what ways can you guys think of where we can see into the human body. So pause the video here. All right. Hopefully you were able to have a discussion with the people at your table and come up with some ideas. Hopefully some of the obvious ones would be ultrasound, because that's what the video that you're watching's title is, but also that's what's on the agenda for today. So hopefully somebody in your group noticed that and came up with that one. X-ray is also a pretty common one because that's something that we were talking about last class. So again, hopefully somebody came up with that. There are a couple other ways that are pretty commonly thought of, and that includes things like CAT scans, PET scans, CT scans, even something like surgery, right? Cutting into the body and opening it up. Obviously, that's a little bit more invasive than some of these other methods we've been looking at. So today we are obviously going to be learning about ultrasounds and how ultrasounds work. We're going to spend a little bit of time looking through a math practice worksheet and kind of reviewing how to do some of the wave math. And you probably can see on the agenda that we also have a quiz next class. And for you guys, that's going to be when we return from spring break. So you do have some time to catch up on some of the stuff if you don't know it, but you definitely want to know it before the quiz. And as usual, we will do a little bit of review before the quiz, but it's not enough time to learn this stuff for the first time. So you definitely want to know this before that, and then just use that review time as a way to remind yourself what's going on before the quiz. The things that are going to be part of the quiz include the wave vocab. So making sure that you're aware of and you know how to use all of the vocab for waves. Those are things like crests and troughs and wavelengths and frequencies and wave speed and direction of wave propagation and direction of oscillation, all the stuff we talked about at the very, very beginning. If you're unsure about any of that stuff, obviously going back to the beginning of the slides and looking through that stuff will help remind yourself. You should have it in your notes, so that would be a better place to look as well. The next thing that shows up on the quiz is stuff from the Wave Lab. So making sure that you are aware of what was going on during the Wave Lab and that you're able to kind of answer some questions about that. So these things would include anything from that simulation. So knowing the simulation, knowing the direction the waves propagate, the direction the waves move in the simulation, knowing the direction that the particles move, right, the direction of oscillation, knowing how to measure the speed of the wave, knowing how to measure the wavelength or the amplitude, looking at the dials on the bottom, right, and being able to identify the amplitude, the frequency, the damping, those types of things. So really just being aware of how to use that simulation. The Wave Lab also uncovered two relationships for waves. The first was that if we change the frequency, that the wavelength of the wave does change. And if we increase the frequency, it decreases the wavelength. And that's that inversely proportional relationship that we discovered. So again, hopefully you remember that and are able to kind of look at that situation. The second situation was where we changed the frequency and we were looking at the speed of the wave. And we realized that the speed did not change. Didn't matter how much you changed the frequency, the speed of the wave did not change. And that's a horizontal relationship. Again, just showing that the speed doesn't depend on that frequency. The last thing that shows up on the quiz is some of the wave math. And we're going to get more into that at the end of class today, where we go through some practice problems, and then we look at finishing up a worksheet on that topic. All right, now we're going to get into our Day 8 link and see what we're looking at. All right. The first thing, again, is going to be one of the think, pair, shares or think, turn talks. And there are 3 questions that we want you guys to be thinking about and talking with your table groups. The first one is, what do you already know about ultrasounds? Have you ever had an ultrasound, especially if you've had an injury or something like that? And then the last one is, what do you already know about waves that you can then apply to understanding how an ultrasound works? Or what do you already know about echolocation that might help you figure out how an ultrasound works? So go ahead and pause here so that you guys can talk through those things with your group. All right. Hopefully you guys were able to talk through this with your group. And the idea of how an ultrasound works, we're going to get into more today. But really, the basic idea is very similar to the way that echolocation works and the way that we talked about echolocation last time. All right, so we're going to look at the role of ultrasound medical imaging, and we're going to watch this video.
Hello, welcome to Wolverhampton Wanderers Football Club. I'm Phil Hayward, I'm the head academy physiotherapist here, and come on in. This is the first team dressing room where the players prepare for training. Come through the dressing room. This is where we have the contrast baths. Following training, the players will tend to do 5 times, so 5 lots of hot, cold, between the 2, just to really get that blood flowing through and get everything flushed out of the system.
Steve Kemp, Head of Medical Services, Wolverhampton Wanderers Football Club. My role is to highlight the players at most risk, address these risks, and then hopefully return them to sport and reduce the injuries in the football club.
So we're in the doctor's office. Here one of the players is having a scan of his patellar tendon using the dual screen function. Everything that we do has an element of science in it, really.
Birds, singers, lorries, guitars, trumpeters, cats, lawnmowers, vuvuzelas, all make sounds. We can hear them because their frequency is between 20 Hz and 20,000 Hz. Although, old grannies sometimes can't hear everything. Anything higher than 20,000 Hz is called ultrasound and sounds like this. Unless you're a bat. But although you can't hear ultrasound, thanks to physicists, you can use it to scan pregnant women, and in this case, footballers' knees.
We're all trained in ultrasound. So I'm just putting the gel on. The gel just provides a medium through which the sound waves are able to be conducted. So at the top there, then you can see your tendon coming down. Just a little dark area at the bottom of your kneecap there, where that pain's coming from.
Pain started coming on gradually after training. It'd be like a bit sore, but like I'd struggle to like fully flex my knee, and then like it just kept getting worse and worse.
We're very fortunate to have this type of equipment here, and not many football clubs actually have it. In a normal situation, you tend to have pain, and you're sort of making assumptions as to what's going on in the tissues, whereas we've got the facility to look on site.
The method of ultrasound is just the sound waves, so it's actually sending the sound waves through, and look, as they reflect back, they give a different picture, and then we know what we're actually scanning through the different images we see.
Ultrasound waves are sent into the body. The useful thing about sound is that it reflects. Hello, 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 hello. So when the transducer sends sound waves into a knee, some of the sound is reflected and some absorbed, depending on whether it hits skin, muscle, water, or bone. These echoes arrive back at the transducer at different times and are analyzed by the computer and converted into a moving image.
The different tissues within the body will transmit the sound waves at a different speed and reflect back at a different intensity. If you stood very close to a wall and said something, you may wouldn't hear that echo particularly well. If you stood a long way back, you'd hear a time lapse between you saying something, hitting the wall and bouncing back to you, and that'd be measurable, and you'd be able to accurately calculate your distance from the wall. So this is very similar, so you can calculate the depth and type of tissue depending on what the intensity of the sound wave that you see back on the screen there. The transducer is made up of lots of little crystals aligned in there, some crystals sending out the waves downwards and then some receiving the information and the reflection or the echo back.
Why use the gel? Without the gel, most of the sound waves wouldn't penetrate the knee, but would be reflected off the skin surface.
The greatest benefit with ultrasound is it's real time. You can actually see the muscle moving, you can see the muscle contracting, you can see the muscle stretching. No health risk at all, so we can use it for long periods of time without any undue risk to the player.
You can see the different layers of tissue are shown. The transducer will be up there looking down, so here's his skin, subcutaneous fat layers, the kneecap there, which is the sort of lighter area, and then his tendon is this nice sort of grainy longitudinal tissue there. And this sort of darker area is where Sam has a bit of a problem with his patella tendon, whereby through overuse, he's just had some inflammation there. It's become a chronic problem, and he's now got poor quality tendon tissue in there.
Ultrasound is great for looking at footballers' knees. Knee injuries are all too common. And by looking into the tissues using ultrasound, physios can not only help players get better quicker, but change their training program so the problem doesn't develop in the first place.
Patella tendons tend to be the biggest issue that we use the ultrasound scanner for.
Football is often a one-leg sport, so a lot of jumping, twisting, turning goes through one tendon. If the athlete has injuries or has weaknesses in different areas, the tendon may not function in its biomechanically correct position. Might develop microtrauma, which is tiny tears to the tendon, which is fine, and the body will re-heal these if it's given time. If it's a professional athlete and he doesn't get time to heal, then that microtrauma becomes macrotrauma and develops injury.
The scanner is very useful for those particular players. It gives a really good idea as to the state of the tendon that you wouldn't be able to identify without that equipment. You can certainly get an idea of how much pain somebody's got just from using your hands, but if you can actually get a quantifiable image of what the tendon looks like, it's much more useful and much more helpful to our practice. So this is the gym. We've got quite a lot of cardiovascular equipment which the injured boys tend to use. I'll show you this piece of rehabilitation equipment which we have, which is known as the Ultra-G treadmill, a treadmill which allows you to run at a certain percentage of your body weight, almost like a reverse vacuum if you like, to blow air into a skirt, and the increased air pressure in the bottom part of the treadmill actually lifts the player up. If you look at a lot of the equipment that we use, there's a scientific background and basis behind all of it really, and everything that we do, we try and make sure that it's evidence-based and that it's scientifically proven to work, otherwise there's not much point in doing it. There is quite a lot of physics involved, and having not taken that as one of my A levels, I probably did find it quite difficult at first to get my head around some of the concepts. Maybe had I known then what I know now and where my career might have taken me, it would have helped me and given me a bit more of a background.
Myself, I've done 2 degrees and 2 masters, and I'm continuing to go on to PhD level. I think that's really important, and all the staff here are now at masters levels. It's something we encouraged. I think everyone's aware football is a growing industry and worth a lot of money now, and you can't just turn up and do the job. You need to be qualified.
All right, so that was a good way to see how, again, the stuff that we're learning in class can be applied to the real world and how people actually use that. Now, one of the key things about ultrasounds and about waves is that the way that they work is because the wave will be traveling, and then any time that there is some sort of boundary or change in the material that the wave is traveling through, some of that wave is going to get reflected and some of the wave is going to get transmitted through. We kind of ignored this when we were talking about echolocation because the bat just wanted to be able to find the moth, And so we really just cared about that reflection off of the moth. We didn't care about the part of the sound that would have continued traveling through. But in this case, that part that's transmitted is just as important as that reflection. And we'll kind of see why here in a little bit. But again, we're going to get a little bit more into the nitty gritty of how ultrasounds work on this next video. It's a super short one, but again, make sure that you guys are paying attention to this.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
All right. So again, now we've got some of the understanding that goes along with how ultrasounds work. We're going to, again, just kind of recap some of this stuff real quick. And we're going to be looking at sort of the more common example that most people are probably thinking of, which is looking at a baby inside of a mom. So for this, the way that it works is, again, we'll rub the transducer along the belly so that we're able to then image the fetus inside of the mother's skin. Now, the first thing that we want to kind of look at is sort of how all of the parts work. And again, I know it was talked about in the other videos, but we'll look at some of the more detail here. So the first thing that the transducer is going to be doing is trying to figure out how deep the signal is bouncing back from. And the way that we do that is, again, very similar to what you guys did last time when you were looking at the echolocation and the bats, but also when we looked at the problem with the well and yelling down into the well. So the equation, the basic equation that we're going to be using is just that distance traveled equals wave velocity times time equation. And so all we need to do is look at the time, and the transducer will know, like, okay, we sent the wave out at this time, it came back at this time. That difference in time multiplied by the speed that the wave travels through the skin or the mother's belly or whatnot, and we'll figure out the distance that the wave traveled. But if we remember from the or the well problem or the echolocation stuff, the distance the wave traveled is not actually what we want. We want, in this case, the depth. And that is half of the distance the wave traveled. Because remember, the wave has to leave the transducer, reflect off of the change in material, and then bounce back to the transducer. So it went twice as far as we actually want. So we have to divide it by 2, which is where we get this depth equation, depth equaling wave velocity times time divided by 2. All right. Again, we're going to sort of look at that situation, but more importantly, we're also going to look at that second thing that we were talking about earlier, where some of the wave continues on, is transmitted through. So again, we're going to start sending out a signal. That signal is going to be traveling. And as soon as it comes across a change in this case, a change in density, then a good amount of the signal is going to get reflected back. And some of the signal is still going to get transmitted through. And we'll see that. right? Some of it getting reflected, some of it being transmitted. And then we can kind of keep going. And the signal that got reflected off of the front of the skull has finally reached the transducer again. And it records the time, it calculates the depth of that pixel, and it knows where that signal came from, the depth of where that signal came from. But just as importantly, the other part of the signal, the part that got transmitted, is still moving along. And when it gets to the back of the baby's skull, it again is going to reflect because it's changing again densities from skull material back into that fluid. And so again, that reflection is going to eventually make its way back to the transducer. And again, the transducer is going to be able to record the time that it took and create another pixel at that new depth. The more lines that we have, the more crystals that we can put in the transducer, the clearer our image is going to be. So again, the goal here is to have as clear a picture as possible. And just like your monitor or your TV screen at home, the more pixels that are on it, the clearer the image can be. So again, lots and lots of those crystals are in the transducer, which gives us a pretty good image. We talked briefly about where this gel comes from and why it's used. And so again, we just want to kind of remind ourselves of what the purpose is. And if we remember, the transducer sends out these signals and they get reflected whenever there's a change in density. Now, unfortunately, there's a huge change in density moving from air to the mother's skin. And so if there wasn't gel there, right, we would go from air to the mother's skin and have a huge reflection, and most of the signal would actually get reflected back immediately. The problem with that, of course, is that we don't really want to see the mother's skin. We want to see what's inside. And so putting the gel here allows us to transmit a signal from the transducer through the gel, through the mother's skin, and not even notice that there's a change in density going from gel to the mother's skin. And that allows the signal to just keep going through and not get reflected back at the skin barrier. That way, most of the signal goes straight through, bounces off the fetus, and we can actually get an image of what we want, which in this case is the fetus. All right, we're going to have you guys again pause it here. I want you to write down the key steps in ultrasound imaging. If this makes more sense to you guys as a list of steps, great. If you'd rather write it as like a short paragraph, a summary type of thing, the way that we did for echolocation and bats the other day, you can do that. Again, whichever method makes more sense to you is totally fine. But go ahead and pause here while you work through that. If you need to go back and look at any of the earlier videos to remind yourself, please do so. All right, hopefully you had time to go ahead and write down your key steps. We also briefly want to talk about some of the benefits of using an ultrasound as opposed to another imaging technology like X-rays, for example. The main sort of benefits here are real time, right? The X-ray, you take one picture, you get one snapshot of what's going on. But some things you actually want a live video feed, something like a heart moving, right? If you want to see the heart beating, it's a lot better to be able to take that video. The next thing is that it's able to image things like soft tissues. X-ray is great for looking at bones. But if you actually want to see muscle, like the heart, or muscles like in the knee, or ligaments or tendons like in the knee, then it makes more sense to have something that can actually see those things and not just the bones. So an ultrasound is beneficial for that as well. The third key reason why ultrasounds are so useful is that it doesn't have ionizing radiation, right? So this footballer, right, he can get his knee ultrasound every single day, and there's no risk of injury because of the ultrasound, right? He's not going to get cancer because of the ultrasound or anything like that. So the benefits, again, being able to reuse it a lot, being able to image soft tissues, and being able to get that live video feed. All right. Now we're going to get into some math practice. So at the very top here, we've got wave speed equals wavelength times frequency. That's the equation that you guys came up with. It is rearranged a little bit, but this is the equation that you guys came up with from the lab. And again, we just rearranged it because we're all at different levels of math, and the equation's just a little bit easier to use when it's in this format. But we will look at changing around the equation so that we can use it for different things. A lot of times we don't want to write this whole thing out, so we have symbols that represent each of these things. Wave speed or wave velocity is represented by a V. Wavelength is represented by this sort of upside down Y. It's called a lambda, but that wavy looking symbol. And then frequency is replaced by an F. So that way we can just write the equation as V equals lambda F. We've got a little table here that kind of reminds us of that the symbol V stands for wave speed or wave velocity. The units for that would be meters per second, again, because it's looking at a speed, so meters per second, distance divided by time type of thing. And oftentimes we'll just write m/s to represent the meters per second. Lambda, this wavy looking symbol, stands for wavelength. And because wavelength is just a distance, it's measured in meters. And oftentimes we just write m, again, to just show the meters. F stands for frequency, and the units for frequency are hertz, which is just a fancy way of just saying per second, right? Because if you remember frequency, we're looking at how many, in this case, how many waves pass a given point in a second. So if 5 waves pass a point in a second, then the frequency would be 5 hertz, or 5 per second. And we often abbreviate that with just a capital H, lowercase z. All right, so let's get into some practice problems and see how we use all this stuff. So here's the first problem. A wave has a frequency of 50 hertz and a wavelength of 10 meters. What is the speed of the wave? So we've got our question, right? And we want to look at how to answer it. And the way that we want you guys to answer it is by doing all of these steps. And I know it's going to seem like, oh, why do I have to do all these steps? It's for a number of reasons. I make my AP Physics kids do these steps, so don't feel bad about it. First off, we want to list off the variables. In this case, we've got 3 variables, F, lambda, and V. And you can put them in whatever order you want. This sample problem is kind of putting them in order that they show up in the question, but you don't have to. When I do it, I always write them in the same order. I always write V lambda F, V lambda F, no matter what the problem is. The next thing that we want to do is we want to start filling in some of those values. So in this case, when we read through and see that the wave has a frequency of 50, we go ahead and put F equals 50 hertz, right? We fill in the 50 hertz to go with the F, the frequency. The next thing we find is the wavelength of 10 meters. So we'll put in the 10 meters with the wavelength. And the last thing is it's saying, what is the speed? So we're trying to figure out what the speed is, so we put a question mark there. And you are going to want to have this set up on all the problems that you work on the worksheet. And you're going to want to have these problems set up this way for the quiz as well. Again, this is showing me that you're able to see the problem and pull out what each piece of information means. The 50 hertz means frequency. The 10 meters means wavelength. The question mark means we're trying to find the velocity. The next step that I have my students do is set up the equation. So in this case, we're using the equation V equals lambda F. On the quiz, you guys would be given that equation. So you don't need to memorize the equation, but you do need to know how to apply the equation. In this case, we have it in the form that we already want it because we're trying to find V, so it helps to have V by itself. We replace each of the parts with the things that we know. So in this case, we know that lambda is 10. So I'm going to replace the lambda with the 10. I'm going to replace the F with the 10 or 50. And so now I've got, instead of V equals lambda F, I have V equals 10 meters times 50 hertz. 10 times 50 is 500. The units for velocity, because that's what we're trying to find, or speed, is meters per second. So we can go ahead and put the units there. So our answer ends up being 500 meters per second. All right, we're going to go ahead and look at the next one as well. Again, I would start off by listing my three variables. Again, they're doing it in a slightly different way than I would, but I would just do V lambda F, V lambda F. All right, a wave has a frequency of 5 hertz. So we can immediately go ahead and fill in wherever we put frequency, we'll put in the 5 hertz. And a speed of 25 meters per second. We fill in velocity equals 25 meters per second. What is the wavelength? Question mark with the wavelength. Perfect. Even if the question didn't say wave has a frequency of 5 hertz, even if it just said 5 hertz, right? We would know that that's a frequency because hertz is the units for frequency. And we know that this is a speed because meters per second is the unit for speed. So now we've got our frequency, 5 hertz, our velocity, 25 meters per second. We're trying to find the wavelength. Well, we have our original equation, V equals lambda F, but it's not super useful in this format. We actually want the lambda by itself because that's the thing we're trying to solve for. And just in algebra class and all those other things, when you're trying to solve for x, you want to get it by itself. And so that's what we're going to do first. We're going to get the lambda by itself. Right now, lambda is being multiplied by f. So we're going to undo that and divide both sides by f. So if we divide both sides by f, lambda is now by itself, and the v is divided by f. So we have lambda equals v divided by f. And if that looks a little weird to you, that's okay, right? If we were to multiply both sides by f, we would get back to the original equation. But we like it in this format, especially for this question, because then we can replace v with 25, we can replace f with 5, and then we get 25 divided by 5, which is 5, and the units for wavelength are meters. All right, we've got another sample problem that we're going to go ahead and look at. In this case, we have a wave with a wavelength of 10 meters. So again, we can start filling in the things that we know. Wavelength equals 10 meters and a speed of 340 meters per second. Again, we can fill that into our values of knowns. We know V equals 340 meters per second. And it says, what is the frequency of the wave? So frequency, question mark, we don't know. We're again going to start with the same equation that we started with before, V equals lambda F, but this time we want F by itself. F is being multiplied by the lambda, so we want to undo that and divide both sides by lambda. It'll cancel out by the F, and we'll get the F by itself. And then on the other side, we have V divided by lambda. We can plug in the values that we know. V is 340, lambda is 10, 340 divided by 10 is 34. The units for frequency are hertz, so 34 hertz. For the problems on the practice worksheet, again, make sure that you guys are showing all of the steps. The steps are super important. It makes it clear to me that you know and can pull the information out of the problem, and I can see the steps that you're taking. So if you end up doing something wrong, I can see where you made that mistake. All right. Go ahead and work on that math practice problem worksheet. When you do get decimal answers, again, that's totally fine, right? In science, we get decimal answers. That's nothing to be scared of. Round it wherever you want. Totally fine. Round it to the nearest whole number, round it to the nearest tenth, kind of whatever feels right for that problem is totally fine. Make sure that you guys are either using calculators if you have a calculator, or using your Chromebook as a calculator, but no phones for calculators. All right. If you do finish this worksheet early, again, make sure that you are double checking the Google Classroom, seeing if there's any missing assignments that you need to finish or complete. And if you do end up helping somebody else with this worksheet, make sure that you are in fact helping them and showing them how to do the problems, not just helping them get the answers. Remember, the process is the important part, not just the answer. All right. Hope you guys have a great day. Hope you have a good weekend.